Hi, everybody. In this recording, I will go over a few central concepts in synthesizing control protocols for cyber-physical systems. So these will typically be hierarchical control protocols, and I will not try to get into every little detail, but I will try to go over some of the main concepts that pop up in this context. And hierarchical control protocols are relatively universal in a lot of applications, in a lot of engineering applications, definitely in cyber-physical systems and in also autonomous systems. And in the background, I will be using this autonomous navigation type example as a running example. So I'm planning to give you some of the ideas behind the solutions that had been proposed over the last couple of decades for a synthesis problem as shown on this first slide. So this is what we will be able to, we will talk about. So it's just a sample problem, and it is given, it is going to be stated whenever it makes sense. I will try to relate it to autonomous navigation, autonomous driving, and other autonomous navigation examples. So it is a problem where a couple of things are given. So we have a system. We may be trying to control an autonomous car or some other system, and the model is going to have a couple of elements to it. It may include what I'm going to call a dynamical system model that is going to have both continuous and discrete evolution, and we will look into this a little bit more carefully. We will have certain control authority in the system, but there will be limitations to that. And very often we will not have a perfect model, so we will have modeling uncertainties and disturbances from outside. And so that's going to be the model side, and the specification side, essentially, what we want the system to be able to achieve. The high-level requirements and goals will be given in some form, and the requirements might be coming, for example, in this application from a driver's handbook. We might have a prior mission in mind that is given over a course map or some other representation of the environment. And the system is going to be operating in a dynamic environment that is going to be affecting whether the system can stay safe, whether it can satisfy the requirements, achieve its goals. And therefore, we will need to narrow down in what kind of an environment the system might operate, and the specifications will include also knowledge about the assumptions that we can make the a priori unknown. We don't know how the environment is going to be evolving, but we will be making assumptions on how it may be how it may evolve. And again, it is going to be a dynamic environment. Things will change, and the system will need to react to it. And the goal is, to some extent, if possible, fully automate the synthesis of a control protocol. And we will see what the protocol refers to in this context. That is going to manage the behavior of the system. It's going to tell this car how to navigate. And it will need to react to the changes in the external environment. And we want to be able to have an argument, obviously consistent with what we have been given. We want to be able to give a proof that the system is going to, if we follow the synthesis procedure that we will describe in these notes, if we follow that, the outcome is going to be provably correct with respect to the requirements obviously we set in the problem statement. So this is the rough problem. And one, it is not mathematically stated yet, but also even at this level, we can see that this problem does not necessarily live in the comfort zone of a single field. There are things that resemble, we might want to go to formal methods, but then also these elements that, hey, we might have continuous state variables, modeling uncertainties, disturbance, etc. That also resembles that it might as well be connected to controls. So that is essentially the difficulty. The problem does not belong to one field. and therefore we will need to make connections between ideas from multiple fields. And in this set of notes, these connections will be roughly made between controls and formal methods. So for a controls person, then we would need to introduce a language in which we may be able to specify the properties that we care about. But then the models that we are familiar with more on the formal method side by themselves may not be sufficient, and we might need to evolve them a little bit as well. So a couple of slides now will touch on these. For those of you who know what these things are, obviously it is going to be not new, but let's briefly mention. First of all, we need a specification language in which we can state the properties that we care. The requirements in, for example, the driver's handbook a autonomous system might have to follow are not properties that a controls person usually deals with. They are higher level, they are much richer than a typical control system is required to behave. And so this is one of the revolutions that the formal methods and theoretical computer science made probably decades ago, and much later on in the context of cyber-physical systems or hybrid systems or connections to controls, had the formal specification languages, their utility had been realized. So I am going to refer to very vaguely temporal logic. I'm not telling what version of temporal logic that we will be dealing with, but temporal logic is essentially going to give the working ground for us to obviously reason about infinite sequences of states of the system, and the state in this context is everything that we care about, everything that can influence the correctness or the safety of the underlying system. It could be the properties at each instant of the system that we are controlling, but also we will take a snapshot of the entire environment that is relevant, and that snapshot is going to constitute the value of the state at that instant. And obviously there are many different dialects or versions of temporal logic, and in this talk I'm not going to get into any of them. I'm hoping to get to touch on the different versions of temporal logic and how they might be utilized in the context of cyber-physical systems in the other recordings. Today, mainly linear temporal logic, but very quickly we will actually narrow down from linear temporal logic even further. And obviously we will use these languages to specify safe, allowable, required, or desired behavior of the system and the environment itself. And so in the context of a little navigation example, we might use these languages to write down that we don't want our system to collide with anything. We may want to obey the speed limits. We might want to specify which lanes the vehicle can be in. If it is blocked, what might be the options? What are the requirements or restrictions at intersections, stop lines, etc. And also the goals of the system might be specified as to reaching some point or reacting to something in such a way that if something happens, then eventually we want the system to be able to go and do something useful. And the environment assumptions in this context, for example, that the intersection the vehicle might arrive at is going to at some point be empty. If the intersection never clears, we obviously will not be able to find a control protocol that would ever get the vehicle through that intersection. And any reasonable intersection will at some point clear, and we should be able to specify that in the statement of the problem, so that we end up having a solvable problem, synthesis problem, if there is a protocol that can achieve the requirements that we have. And the list goes on. We might list a couple of things about the sensing range of the vehicle and its ability to detect the obstacles. We might know that the obstacles around the vehicle are other physical objects that cannot, for example, teletransport themselves, or they cannot disappear at some point and then pop up instantly at some far distant point. But we should be able to specify these things, and the work in this area has been using variants of temporal logic for this purpose. Okay, so this is, and then obviously these things are not specific for only one application. Autonomous navigation is one. This is another multi-vehicle air vehicle in this case, multi-air vehicle navigation scenario, and it had been integrated into a user interface through which one can specify what missions multiple air vehicles may need to deliver for different purposes, and in this case, what coverage area, in what sequence the goals need to be achieved, the coordination between multiple vehicles so that they don't arrive at the same point at the same time, etc., can be specified using temporal logic. Okay, so that is one point. The other point is that formal methods are the bread and butter of system models. It would be fair to say that in formal methods, more finite state representations of the systems. And we often encounter evolution of systems that for which merely finite state evolution, discrete jumps, may not be suitable or sufficient. And in the intersection of what controls had been studying more based on differential equations or difference equations and finite state representation on the other side, the notion of hybrid systems had emerged. And it essentially mixes these two things. And in this slide, I have an extremely simple representation of a hybrid system model. It is a tuple where we specify the states, both the discrete and continuous states, and specify how the continuous state evolves and how the discrete state may evolve. And in this one very simple representation, essentially the discreteness of the system is coming from that the continuous state space had been is partitioned into regions, and in each region the underlying differential equation is different. So the system follows a continuous a differential equation or a difference equation for the evolution of its continuous state, and whenever it actually changes from one region to another, where the labels of these regions may represent the discrete states, it changes the differential equation or difference equation it follows. So I'm not going to get into details. So that is essentially the main picture. For each region, you may have a different. Let's say X is the continuous state, a different differential equation. In this region, it may follow F1, the vector field, and in this region, it may follow some other differential equation where the vector field is different. And it can be much richer than this, this description. But for the purpose of today's notions, it won't be too relevant. So I'm going to go with this hybrid system model for now. Essentially, it is switching between different vector fields over the state space, continuous state space. Okay. With that, in what ways do hybrid system models arise? So a couple of comments could be made about that, and not all of these will become relevant for our purposes, but I thought it might be useful to remember. So one way that may appear is that we might have actually a fully continuous state space, but the system dynamics might be too complicated for analysis or design purposes, and we might use piecewise affine representations. It does not have to be affine, but essentially over different parts of this continuous state space, we might choose in a localized manner to have simpler dynamical system models, and then we patch them, and the switching essentially induces the hybrid nature of the system. We might have impact from outside. in the form of discontinuous jumps in the dynamics. For example, in this bouncing ball example, the ball is under the influence of essentially the gravity, but every time it touches the ground, it has a jump, and in its speed, and that induces the hybridness of the dynamics. The hybridness might come essentially. One sec. The hybridness might come from the way that we actually control how we observe the system, and then how we choose to control it, and it is referred to as a quantized control. We may choose not to see all the details of the continuous state space, but we might want to look at this through the lens of a quantization of the underlying state space or the control space. We may have logic-based switching, and a canonical example, a good example for this is this collision avoidance. Two aircraft flying in certain ways, but if they get close to each other, there is an underlying protocol that abruptly changes the evolution of these two systems so that they avoid each other. And another way of which is going to be very relevant for us is that we may have a continuous or some sort of continuous state evolution, but the specifications may be discrete. And this discrete specifications is in quotes. It is essentially referring to roughly that they are specifications for which we have means to analyze or design. If the rest of the system was discrete, for example, temporal logic specifications given over a finite state model, that we know, or we are more confident how we can analyze such systems and design for such systems. But now if one side has continuous evolution and we have temporal logic like specifications, neither field has the right tools for it. So what I'm trying to emphasize here is that there's a mismatch between the representation of the different parts of the system, and that results in notions of hybridness in the underlying representations. Okay, so with that, let me just remind you what the problem that we will be studying in this recording. It is just a slide repeated, but now instead of having this vehicle picture, we will have a sort of a hybrid system model that represents the system. And then specifications, we will use versions of temporal logic to represent the specifications. So with that, we can actually now we can try to develop algorithms, because these two elements will help us to write down mathematical problems that we can study. And before doing that, let me just discuss a tiny bit on some of the different approaches for analysis and verification and synthesis for hybrid system models. So, and essentially, the one thing that we need to realize is that for systems that have continuous state spaces, exhaustive search is not going to be possible. And so we cannot directly apply the ideas from formal methods. On the other hand, the several approaches that we have seen over the last couple of decades are essentially taking, hey, I know I have the tools for analyzing finite state models. Let me make a finite state system out of this otherwise continuous space, state space representation. So they rely on constructing finite state approximations of the underlying dynamics and then apply the tools that can be used for finite state models. So I would say that, hey, I have a problem outside the domain of formal methods. Let me do something, pull it into the formal methods domain, and then see what I can do there. And then obviously we will wrap things around it. And so while finding these approximations, we need to pay attention to that as we approximate the systems, we do not lose the meaning of the properties, or if we have a property over one representation of the model, but analyze or design with another representation of the model, the specifications given on this side should be able to unambiguously interpretable on the other side. And then approximations should have certain properties for yielding meaningful results. So we'll look into that as well. So this is one approach. Essentially, this is, hey, I'm a formal methods person. Give me a hybrid system model. I'm going to pull it to my side. I will crunch it using my tools. The other side is the controls, mostly controls approach, I would say. Hey, I have tools to deal with infinite state, continuous state problems or systems. How can I pull this hybrid system question to my side and then try to crunch it with my tools? And I'm going to summarize it under this, what I'm calling deductive techniques. Essentially, it takes the underlying system, since it cannot go and enumerate or to represent every single state of the system or every possible evolution of the system. We would have to have an alternative approach, which is try to construct so-called algebraic certificates. So try to find a function that satisfies certain properties, and after that it actually witnesses the satisfaction of the property that we care. And Lyapunov functions, barrier certificates are examples of these things. If there's a controls version of it, obviously various ways of approximating so-called value functions will be relevant. And then the underlying hybrid dynamics usually have these discrete jumps. So we will try to deal with that in some way. Essentially, extending the notions of these algebraic proof certificates to deal with the existence of different regimes or different regions in the state space in which the system behaves differently. A third approach is essentially trying to somehow, just between these two, not necessarily enumerate one by one all possible features of the system, but somehow explicitly construct a set of reachable states. Starting from some initial state, somehow represent this the set of initial states, find these tubes or at each instant where this system might end up, try to represent these set of states and propagate them either forward in time or backward in time, and then see whether they intersect with some unsafe set, or whether they ever have intersections with some desirable points that we might want to reach, etc. So the point is that explicit representation of the set of states in which the system might end up being. So I'm not going to touch on this one too much today. In this recording, I will go in this direction in the first one. And if time allows, I am planning to have another recording on these deductive techniques. Okay, with that, let's see what the next slide is. Okay, so as I said, the approach is going to be somehow make a finite state approximation out of the given hybrid dynamics. For the discrete part, we don't have to do much, but for the continuous state evolution, we somehow need to make it finite. And then we will need to have certain properties in this finite approximation. And roughly, I'm going to call these things as under and over approximations of the underlying system. So we have a hybrid system model. Just this picture I'm going to carry around, and then we are given a finite transition system. For simplicity, I'm not having an extra controlled input in these representations. So we might consider that somebody already gave you a controller. The extensions are not too complicated. It is just going to be, I cannot fit them into one slide. So let's just live with this. So we will try to make a connection between these two representations. And the first thing is essentially the states of the finite transition system will be these QIs. And we will associate each QI with one region in a partition. Let's say we already partitioned the underlying continuous state space, and we will touch on how we might partition. But let's say for now we have a partition, and for each cell in this continuous state space, we will associate a discrete state QI. And then this T essentially is a map from the discrete state to the top subset of X to which the Qi corresponds to. TQ1 is this region, for example. TQ2 is this region. So we will have that. Then we will go and we will now ask, once we have these regions and the discrete states, we will try to define or choose the transitions between the states in such a way that we can have the desired relation between this hybrid system H and the finite transition system Q. Sorry, TS. And here's one statement of it. We will call the TS an under-approximation of H if these following two statements hold. Essentially, let's try to read it. So given Q and Q prime, the two discrete states, they are not the same. If they are the same, we will treat them differently. If there is a transition from Q to Q prime in the finite transition system, then let's pick two states, two regions here. Let's say one region is this is Q, and this is Q prime. Then for all initial states in Q, all initial states, all points in this, there exists some time such that the system ends up at the end of that time period, tau, the system ends up somewhere in this region, in the region that corresponds to Q prime. And for all times between the initial time and this tau, the end of the time horizon, we have to stay in the union of these two. All right. So essentially, for all states in the initial, in the region that corresponds to the transition, discrete transition, we are emanating the discrete transition from Q. For all initial states in the region that corresponds to Q, we should be able to find an evolution up to some time tau that ends up in the region that corresponds to Q prime. And for all those times, we want to stay inside this region. So then, if we have that property, we will have a transition from Q to Q prime. And there is a possibility for a self-transition, and that's going to happen if the region that corresponds to Q is positively invariant. That is, in all future times, we essentially don't leave that region. So if we restrict the transition system, TS, to have transitions that are characterized by these conditions, then the resulting TS is going to be an under-approximation of the hybrid system. So that also is going to mean that every discrete trajectory in TS can be implemented by H. No matter where you start here, there is some future that's going to take you somewhere in this region that corresponds to Q prime. It does not matter. You start here, there's something that takes you there. So if we have those properties, that we will call it as an under-approximation. And the over-approximation is the flip side of the coin. It is essentially, we will include a transition, discrete transition, for example, Q, Q prime, and Q double prime. So we have here two continuous trajectories starting from two different initial conditions that in the region that corresponds to Q. One ends up in the region for Q prime, and the other one ends up in the region Q double prime. In this case, in the transition system for over-approximation, we will include both Q, Q prime and Q, Q double prime. All right, so over-approximation looks into a possibility. Is it possible for me to find an initial condition in this region that would take me to Q prime? Yes, it is possible here. Is it possible to go to Q double prime? Yes, it is possible. There's another initial condition that's going to take you there. But they may be different initial conditions. They may end up in different regions, and we will include all these transitions. So this is we are talking about a possibility. It does not say that if I start here, I will be able to go to Q prime. It just says that, hey, is this possible that if you start from some appropriate point in this region, then you will end up in Q double prime. So that's the difference. Whereas in under approximation, if you start from this region, no matter which initial condition you pick, you will end up in Q prime. Okay, so under and over approximations. And for verification and synthesis purposes, both could be useful means. And we will today, for synthesis purposes, we will mostly look into under approximations. So now we have a lot of tools. Let's look at what a solution looks like. Finally, this notion of hierarchical control structure. So it is going to look something like this. And I am going to hide this part. And the reason is that that is too low level for us to deal with. There are zillions of tools in controls to make sure that these systems at very low level behave properly, or if I give a short trajectory, they will be able to follow that, they will be able to go to some point, etc. So we will not deal with that. We will look into this hierarchical structure here. Okay, so let me see. I need to get rid of these boxes. Okay, they are gone. Not sure how to get rid of these things. Let's try one more time. Maybe this time they are gone. Okay, they are gone. So, as I said, we will focus on this or on the hierarchy that we see here. 3 levels. The names do not matter. The point is that there are multiple functionalities that we need to synthesize separately, but in coordination with each other. And the problem cannot be solved in one shot, the synthesis problem that we have. Instead, what we will be doing is we will be having these layers. I'm showing 3, and each layer is going to be working with a different view of the specifications. So the lowest level is going to work with the constraints on the continuous state space and maybe the inputs, and it's going to correspondingly it is going to work with some difference equations. And in this talk, I'm referring to the evolution of time interchangeably with continuous time and discrete time. And these slides for cleanness, but in all implementations, I will be actually looking into discrete time evolution. So if I go back and forth, it is just so pictorially here. But when it comes to implementations or algorithms, we will be directly working with discrete time evolution, and extensions to continuous time are possible. It just makes it uglier, and some technicalities might arise, but the main ideas will mostly carry over. Okay, so we will chop the specifications into different views, and we will pick models abstractions that are appropriate for that view of the specifications. At the lowest level, constraints on the continuous space, and we will be working with discrete space models. Sorry, continuous space models. Then middle level might be the short horizon specifications, and in this case, we might jump into some discrete evolution, and just it's going to go on like that. And depending on what specifications you end up at in each level and what models that you use, obviously the resulting problems that we have to solve will correspond to that. At the bottom level, we will be dealing with constrained finite state optimal control problems, typically. We will choose to reason about the dynamic environment around us at this discrete level that has some implicit assumption on that we look at the evolution of the dynamic environment around us, the other cars, the conditions on the road, the traffic lights, etc., only at these discrete time instances at which we see the system at these states of the discrete model. And then as we go higher up, and then we will end up solving two-player turn-based games. And I will briefly touch on that, and I know you will have seen earlier this week more detailed exposure to such problems. And then long horizon specifications, I say, at a high level. And nothing is actually set on stone. These are just some little examples of how we might want to chop things off in a hierarchical manner. And in this setting, we might think it is as that if this is a navigation, the highest level might be choosing the highways, the streets that we might follow. And then once we have it, the middle level might look into, hey, is the intersection empty? Can I follow this road? Shall I change my lane because it might be blocked, etc.? So that level of reactive reasoning against the environment. And the low level, once we decide, okay, I'm following this lane, so let me find a continuous trajectory. Okay, I need to change my lane. Let me find a trajectory that's going to do that for me for very, very short horizon. So everybody can decompose any given hard problem in any way that they want, right? The key is not that. The key is essentially doing it in such a way that we have conditions between these layers. Conditions between these layers such that there's a consistency between the layers. And this is where the abstractions, the under approximation or over approximation, in this case, we will start from the bottom level and we will go higher and we will try to have under approximations. So that when we put these pieces together, everything is going to be consistent with each other. If this top level issues a directive, right, then the middle level will be able to implement that. And similarly, if the reactive controller says something, there's going to be a continuous trajectory that we can pick and implement, and it is going to accomplish whatever goal, intermediate goal, this mid-level actually set for us. And this description essentially takes care of a couple of things. People often call these things correct by construction. It is just that we will have constructed the models and depict the specifications in such a way that once we solve the problems in each layer, because there's consistency between models and because the specifications, when put together, they actually guarantee that the overall constraints or requirements that we have will be satisfied. By construction of these elements, we will have a guarantee that this overall picture is going to be yielding a solution to the problem that we want to solve at the beginning. So that is going to be the correct by construction part. So what I'm going to do is now look into some of these layers a little bit closely, and then we'll see what happens. So I'm going to start with the middle level. So and it is going to essentially rely on what is out there for reactive synthesis, or we looked into game solving in the previous. We will have looked into game solving in the previous lectures. It's going to rely on that. And it is not a coincidence. So this is from where I have been over the last decade or so. The historical evolution is that, hey, something is happening in reactive synthesis, right? And these problems that we are trying to solve have resemblance. So how can we morph the problems in such a way that we can leverage what is happening on the theoretical computer science side, and we can try to build solutions for bigger problems that we cannot solve otherwise. So the intention was, how can we leverage reactive synthesis? And for this, obviously, we will need a finite transition system. And that is going to be the model that we will have for the middle layer. And then I'm going to talk about one way of obtaining this. So there will be some controlled variables. The specification will be that, hey, I have these environment assumptions. Whenever environment whenever environment is constrained in a certain way, I want my system to satisfy the specifications. These, we can refer to them as assumed guarantee specifications. And there is no doubt that specifications in the form of assumed assumptions and guarantees are the right way of looking into problems in cyber-physical systems or autonomous systems, because all of them actually operate in environments that they cannot control. and the environment is represented by a variable E. So what's going to happen is that the reactive controller is going to observe what the environment has been doing, including the current step that we are at, and it is going to know what has been happening in its own controlled states, and it's going to pick the next controlled variables in certain way that we satisfy the specifications that we have. So this can be formulated as a turn-based game, interactable in general, but much more forgiving complexity for certain fragments of temporal logic, for example, the GR1 specifications, in the form of, again, it is an assumption and guarantee. And the pieces are, we can say, we can talk about initializations, we can talk about invariants or some mild safety formulas, and we can also talk about the liveness or fairness and goals for environment. We can say that the environment does certain things infinitely often in the future, so we know that it's going to come to certain places. And then, given that, whether we can actually get our system infinitely often to certain other places. So syntactically restricted, obviously, but the world is, the name of the game is not only expressiveness. For all these things that we discuss, you can find more complicated hybrid system models, you can find more complicated specifications, but the name of the game is not only expressiveness, it is whether we can have a little bit more forgiving complexity so that we can solve some problems that might have relevance for reality. And GR1 specifications, as I see it, have proven to be actually hitting some useful sweet spot. It does not cover everything, but it doesn't have to cover everything. It has found broad enough applications where it can solve interesting problems. And the resulting strategy is going to be essentially, hey, look at how the environment evolves and pick the next move for the system. And if we look at it, so given a finite transition system, we can take this controller G we have, compose it with M, and we will be satisfying the specifications that we can interpret at this layer. As we have been saying, we will have continuous dynamics, underlying continuous dynamics. We will have system representations more general than finite transition systems, or we may not even given finite transition systems. So how are we going to connect these two? Just the reality or physics of the system is here. Reactive synthesis offers to deal with finite transition systems. How are we going to connect these two? And this is where the continuous controller, or the bottom layer in this pictorial or cartoonish hierarchy I showed. Essentially, it is the layer between what reactive synthesis can handle and what the underlying reality is. And this is where a finite state abstraction procedure comes in, where we will know that the resulting thing is going to be an under-approximation. We already looked into what an under-approximation means, so essentially we will start with the continuous state space, we'll end up with a finite transition system. This is going to be an under-approximation of the given underlying continuous or hybrid state system model. Again, partition the continuous state space, and then associate a discrete state for each cell in the partition. And then we will decide what transitions we can assign. And let's look at this yellow to blue. We already discussed that. We will include that transition if for all initial states in this one, there is a way for us to go to the blue one. And previously, I looked into that with no inputs. When there is inputs, the resulting problem turns out to be a robust set-to-set reachable-to problem. And so the dynamics, let me just actually step back and show you what the dynamics look like. So we have the continuous state space. We have the control input. This is the input, the underlying low-level control input that we can pick to influence the evolution of X. And we are subject to some disturbances as well. So this W we cannot control. It can be, I don't know, some roughness or slipness on the road, or some winds, etc. might be coming and affecting the underlying continuous evolution. So the problem that we are trying to solve is whether there exists a control input u and some finite horizon length t. This is the horizon length that we are looking into, such that for all time instances up to that horizon, the state stays in the intersection of some initial set and some target set. Initial set. This is just we are focusing on whether this discrete transition. We can go from this region to this region with the right qualifiers. There exists a control signal such that we stay in the union of this. At the end of the time horizon, we are in the target set. And the qualifiers are for all initial conditions x0, for all initial conditions here, and for all low-level disturbances. So this is a problem, and the dynamics are given here. This is a problem which is extremely hard by itself. Yes, that's a true statement. It's extremely hard by itself. So we cannot hope to solve it for all possible cases. But research has shown that if the underlying dynamics are hybrids, but within each mode, within each region, for example, you have linear dynamics or affine dynamics, and all the sets that you encounter, this set, this set, this set, this set, all sets that you might encounter in the statement of the problem are polytopic, can be represented as combinations of affine inequalities, then there is some hope. All right, and there are lots of tools out there that look into different, even within this general family, different ways of representing sets, different ways of representing the underlying dynamics, so that just we can scale these things up. And then a little bit more researchy sides, but still we might do something when the underlying dynamics are polynomial and the constraints are, all the sets are semi-algebraic. They can be represented as inequalities on polynomials. Then we can actually start having some upper and lower approximations of these regions, that sets we have to keep track of, and then we may have some hope. And some other side of research is looking into whether there are some underlying properties of the dynamics. The dynamics might be ugly in one representation. They might be impenetrably nonlinear that we cannot deal with. But if we can, for example, transform these dynamics into some other coordinate frame using the so-called differential flatness of the underlying system, then these point-to-point or set-to-point reachability problems might be solvable to some extent much more efficiently. But then this transformation might bring some potential errors that we might need to deal with by, again, dwelling or shrinking these sets that we care about. And so we might be able to come up with, hey, I cannot answer this question, but if this target set was something larger, maybe I can guarantee that there is something in that larger thing. And then you need to then keep track of this data that you gather and build an under approximation out of that. And it might introduce a possibility of errors that you make. Hey, I think this discrete transition is possible, but because of this, there's some possibility that at some point you might not be able to make this transition. So you need to essentially bookkeep all these things. Long story short, this is the problem that we need to solve. This is the problem that we need to solve, and we may be able to solve in some cases, and we might play lots of games when things are a little bit different. Let's say for now that we can solve that problem. Then we can put these things together. Again, this is this picture that we looked into. So what's going to happen is, essentially, by constructing the underlying abstraction in the right way, what we can guarantee is that for any discrete run, and this is coming from this is coming from the fact that by construction the abstraction is under approximation. Any discrete run that satisfies the specification, let's say this is the sequence of discrete states that we follow, and it satisfies the specification because the reactive synthesis tool that I used with the right abstraction, etc., tells me that, hey, you need to follow this. And it satisfies the specification. Then there exists an admissible control signal that generates a trajectory over the continuous state space. I labeled these regions as news, but actually we are now looking into this continuous trajectory. So if there is this, then by construction there is a control signal that's going to drive the continuous states as continuous part of the continuous state, as shown in this lower part, and that continuous implementation will also satisfy the specification. So that is that, and this is essentially just stating what I just said. And then it may not be possible, right? You have this abstraction now, and it turns out that there is no way of finding a reactive controller that's going to give you what you like. Then there may be zillions of reasons for this, one of which is that, hey, this problem is actually not solvable, but then it may be that the abstraction that you have is too coarse that you cannot find, you did not include enough possibilities in your abstraction to achieve what you wanted. Then obviously, a bunch of abstraction refinement techniques, essentially hacked versions of counterexample guided abstraction refinement, comes into play and say, okay, look, from this, I cannot tell you that you will necessarily end up in this. But what I can tell you is that there's a subset of this initial set from which you can go to this. I don't know what happens from this part. Then, instead of working with essential in U5, we say, hey, I am now removing my discrete state in U5. I'm going to put some new 10, new 11. These will be, instead of one, I have two discrete states. I know that from this discrete state, I can go to this one. What happens from this new part of it, I will deal with that separately. So that comes into the refining the abstraction, because you are now looking into regions that are smaller subsets of the original regions. So let me show you some examples. So this is where we want to take it, and to some extent, the last decade of work has been able to do it. So we want to start with some abstract model of the system and some specifications, and then go through this procedure, come up with some code that we can implement on the system, and then push it to some simulation that then see that it works, or even better, to some hardware implementation. I have two examples here. One, this is a quadrotor that we control. These two are not, we don't control them. So we want the controlled quadrotor to visit 3 points repeatedly in the future, roughly at those 3 points. And obviously we don't want it to crash into any of the controlled, uncontrolled, those two quadrotors in the environment. We don't know what those uncontrolled quadrotors will do, but we know that they will actually stay within, one of them is going to stay in that line, and the other one is going to stay in this line. They will go back and forth, and these are physical objects. If it is here, we know that in the next instant it is not going to be able to jump here. So relatively mild assumptions on what they can do, and then we essentially run this procedure that I described and come up with a controller, layers of the controller for the quadrotor that we can control. And at this point, I cannot tell which one is the one that we are controlling. Probably this one is what we are controlling at this point. Okay, so this is one example, and the other one comes from a student who worked on this as a course project. He works on humanoid robots and full body locomotion, and there are essentially cracks. There's first of all, there's this simulated body, that is robotic body that is trying to move. There might be this slippage on this track. There might be cracks. Let me go back and come back to it. There might be cracks on the stairs. It holds the top part of it, and there are cracks there, so it cannot hold. At some point, it cannot fit there, and it needs to slide. So what mode to implement comes from the reactive controller, and how you implement that within that mode comes from the underlying continuous control. And I discussed only one way of coming up with a finite state abstraction that might be useful for this hierarchical view. And there are obviously other ways, many other ways, than we can discuss throughout the program now at Simmons Institute, if you guys want. So here's another example, and I will try to finish this now quickly. Traffic rules, bunch of assumptions on the behavior, and the mission is in this 2-lane road for this vehicle. to visit these two stars infinitely often. So that's the high-level goal, and there are a bunch of other rules that we have. Relatively naive dynamics, but we have limitations on the actuation and disturbances on what the vehicle does. So if we try to solve this problem, just a naive discretization of the underlying continuous state space, not even the state space, just the position space here, right? Just the state spaces, it might have its velocities, etc. Let's look at this discretization of the underlying positions. Just this discretization is going to give for us to deal with 10 to the 87 states in the reactive controller level. Yes, reactive control synthesis has seen some progress, but this is obviously beyond what it can do. So when we faced with this, we said, hey, let's introduce one more layer. And its goal is, it does the following. Let's see how it behaves. Reactive controller takes care of when it is at the intersection now, there's something intersection, it waits. And then the obstacles pop up. When it is a right turn, it actually waited again. When there's an obstacle, it changes its course and it goes to the other lane. Those are decisions that are being made by the reactive controller. There is this top level, and the decisions the top level is essentially making is with respect to these even higher level specifications. In this run, the top level says go around this block in that circular manner, and then obviously you will be satisfying visiting these two stars infinitely often. And then at some point, at this point now, there is a blockage that we cannot do it anymore. And the top level now says, okay, you cannot do it. Reactive controller said we cannot continue here. And the top level now says, okay, now go around this bigger block in that circular manner. Still, you will be satisfying these two, coming to these two stars infinitely often. So essentially, the top level now, the third level, is chopping the problem into shorter horizon constraints. The top level says go around this, and that essentially maps it to a partial order, so that instead of trying to branch out, we have this circular path. We know how to proceed on that, and it helps us to chop the problem into smaller horizon problems that the reactive control has to deal with. It can crunch those things quickly, and then it tells which lane to follow, where to turn right, left, wait, etc. And then the continuous controller implements those things. And extremely quickly, what happens at that top level is that, again, we partition the discrete state space into different regions. And the goal is to very pictorially and simply, the goal is reaching some target states, the goal state. And the relative configuration with respect to that goal gives us a order on between these sets. This set is closer to the goal, this set is closer to the goal, etc. And then the reactive controller, instead of trying to solve this problem directly, it essentially starts, instead of starting from the ultimate initial condition, it starts from where the system is. And instead of reaching the goal, it just tries to get to a cell that is closer to the goal. For example, starting from W4, it is not trying to reach the goal. It is just trying to, for example, reach W2. Because if we could do that, we will be able to actually from there proceed toward the goal. And it is receding horizon, partly motivated by so-called receding horizon control in the control literature, because it plans all the way up to W2, but when it gets to W3, on the way to W2, it says, okay, now let me redo it. I am now in W3. Let me now roll my horizon, and from W3, let me try to get to W1. And if the specification for the middle level is set in this way, and there is this extra piece that we called an invariant, then we can actually go and talk about that this receding horizon implementation of the short horizon strategies will be able to satisfy these specifications. It's essentially chopping the problem into pieces, but then for consistency, again, we need to have a little bit more in the problems that we have to solve. We cannot just chop them into pieces and hope that it's going to work. In order to be able to have consistent evolution, we needed to have this piece of invariant. An invariant is essentially tries to figure out the corner cases, so-called. We don't want to bring, in the solution of a problem, we don't want to bring the system to a configuration from which the next system cannot do anything. If we, sorry, the next problem cannot do anything. If we try to solve the problem in one shot, those things would have been excluded by the reactive control synthesis already. But if we chop these things into pieces for simplicity, then we need to somehow figure out how to avoid those things. And so this is the last slide. So let me put these things, comment on that. Instead of the problem that I motivated was obviously, let me specify something and then use models to the extent that I can, and then synthesize the controller. So let's go from all these models and specifications to a control protocol for which I'm going to have a guarantee, and I'm going to refer to this as specify and synthesize. And a lot of work had been put into the other side of the coin, which is designing and verifying. First design something, maybe even build it, and then try to verify that it's going to behave safely. But lots of examples of cyber physical systems and autonomous systems have shown that there's no limit to human imagination. We can build arbitrarily, we can design and build arbitrarily complex systems. Therefore, first designing and then trying to verify may not be the way to go, because we might end up having an unsurmountable amount of complexity. Whereas through specify and synthesis, we start with what we want, and in each step, we keep track of some precise and unambiguous specifications, what can be done, what cannot be done. And then through that, we can actually, we will have a formal and unambiguous way of expressing what is going on in the system design. And the second thing is that we may be able to suppress the complexity of the system. And it is going to also be more suitable if I'm building up a system rather than trying to work with a system that is given to me. I would have more flexibility to impose architectural constraints that will go and suppress the system complexity even further. For example, we suppress the complexity of the problem by imposing this hierarchical structure on the controllers. And it's not the only way that we can actually try to do this. There might be modularity and composable structures that we might look into, and compositional control synthesis becomes very important. I don't think I'm going to have time in these recorded lectures, but I'm happy to discuss those notions as well. And the biggest benefit from all these things is essentially starting from specifications, having formal specifications and trying to keep track of that, and trying to have these approval guarantees on the end products is, we may or may not be able to automate the entire design flow. We will probably not. But it is going to give us a discipline or disciplined way of trying to deal with this unsurmountable amount of complexity, otherwise unsurmountable of complexity. If we do not have that rigor, or if we don't have unambiguous specifications in each step, it is just going to be a mess. It's just going to be a soup of a lot of things that nobody can interpret. And therefore I chose to talk about first specifying and then synthesizing, because I think that has a much brighter future than trying to deal with some other person's mess that I can try to verify. So here I'm going to stop. I'm happy to discuss any of these things to the extent that you want. Thank you.